that works. All right, so last chapter was about will a chemical reaction happen, and we looked at Gibbs free energy as the answer to that. And today we are jumping into the next question, which is how fast will chemical reactions that can happen occur? So we're looking at chemical kinetics today. Okay, give you a second to write. So thermodynamics was about will it react. Chemical kinetics are how fast will it react. Remember, for the Gibbs free energy thing was looking at enthalpy and entropy, and we wanted a negative delta H value. We wanted chemical reactions to release energy that helps it be spontaneous, and we wanted a positive delta S value. We wanted to increase the amount of chaos in the universe, and then that also helps chemical reactions happen. And then there was that reaction that put delta H and delta S together, the Gibbs free energy equation, which was the delta H value and then the delta S value considering temperature combined into one equation. And if we got a negative answer for that, then we would say that there is a net release of energy. There is more free energy available after the reaction than there was before the reaction, and so a negative delta G meant yes, this chemical reaction will happen. But we don't know if it's going to be slow or if it's going to be fast. If you buy hydrochloric, not hydrochloric acid, if you buy hydrogen peroxide at the grocery store to have in your medicine cabinet and clean your cuts, the hydrogen peroxide naturally dissociates into water and oxygen gas. And that is a spontaneous reaction, but it is incredibly slow. It's so slow that you can have a bottle of hydrogen peroxide in your pantry for years, and it still does its job when you pour it on a cut. But it is ever so slowly turning into water and oxygen gas. Okay? Very, very slow spontaneous reaction, which is very different from lighting off a firework. Lighting off a firework is a chemical reaction that is spontaneous, but it does not fizzle and sit on your shelf for years, slowly going off, right? It goes off and it goes boom, and you don't want that in your pantry because then you don't have a house anymore. So some reactions are very slow and spontaneous. Some reactions are very fast and spontaneous. And the point of the next chapter is how quickly do these chemical reactions happen? Okay? So you're going to be seeing a lot of diagrams in this chapter, a lot of graphs. And the basic concept is we're comparing the amount of energy of the reactants to the amount of energy of the products to one more thing. We're comparing it to the transition state. And so we're looking at the amount of energy required to go from the reactant to the product. Thermodynamic reactions basically looked at the difference between the energy of the reactants and the energy of the products. This is the energy of reaction, or the delta H for the reaction, right? And then delta S comes in there and influences it as well. But everything that we looked at before was about this step in the graph. How much energy is in the reactants? How much energy is in the products? What's the difference? If there is more energy in the reactants than there is in the products, then the reaction as a whole goes downhill, and the reaction is spontaneous and it will happen. But there's almost always a bump in the graph. And this chapter, we're looking at the bump, and we're seeing how big is this energy spike that is needed to get the reaction going. We call that the energy of activation. You almost always have to invest some energy in a reaction to get it to happen. Reactions very rarely just go straight from here downhill to the products. Almost always that you have to add some energy to it. And then you get that energy back out as the reaction progresses. The reaction releases that energy again, and you wind up with a lower energy state and a spontaneous reaction. But there's this bump in the middle, and you can think of it as like a roller coaster. If you got on a roller coaster at the house where the roller coaster, you know, loads, and then the roller coaster didn't first go up a hill, then it's not going to be able to go wee down the hill and have the ride, right? It's going up that hill that gives you the energy to go through the ride, unless you're at California Adventure and you're on California Street and the thing is launched by magnets. But that's new technology. Old times, you had to go be pulled up a hill, and then you got to go wee down the hill, right? This is going up the hill. This is adding energy to the reactants so that there is enough energy to make the reaction happen. And then you wind up at a lower energy state, and this is what we were looking at last chapter. This is what we're looking at this chapter. So here's just another example. This would be an endothermic reaction, where there's more energy in the products than in the reactants. So some reactions are endothermic. We looked at that with a positive delta H. So here you see a positive delta H. There's more energy in the products than there is in the reactants. But if you can give it enough energy to get past the activation complex or past the transition state, it does roll downhill and the reaction will complete. But you had to give it more energy than it gave off when the reaction happened. So this is an endothermic reaction. The one that I showed you before was an exothermic reaction, where the reaction starts at the reactants and ends at a lower energy state product. So this is a negative delta H. The amount of energy in the reactants is greater than the amount of energy in the products. And so you have a negative delta H here, you had a positive delta H in the last slide. And then again, you almost always have to add some energy to the reaction to get it to happen. And then once it happens, it goes. And in an exothermic reaction, it releases way more energy than you had to give it. But you had to give it something at the beginning to get it started. Okay? This is a very rare case where there is not an activation complex, an activation pathway, where the reactants, as soon as they touch each other, react. But this is definitely the exception to the rule. Almost always there's a bump. Okay, very rarely do you see reactants going straight to products. It does occasionally happen. And then again, there's the very rare situation where you add a whole bunch of energy to reactants to get to the products, and then the reaction occurs and it doesn't give off anything else. This would be a very hard reaction to get to happen, right? It absorbs heat and there's no bump, so it doesn't release any energy when it gets done, it just goes straight to the products. These are much rarer than the ones that we saw earlier. Okay? All right. Okay, collision theory. This is the why. Why do reactions happen and why are there these activation complexes necessary? For this idea of the why behind reaction kinetics, the thought is that reactions happen when reactants collide with their active portions facing each other. That if the reactants collide backwards or in the wrong orientation, a reaction won't happen. So the active part of the molecules have to bump into each other in order for the reaction to happen. So there's the orientation question, and then there's the enough energy question. We can't really control the orientation of molecules that are floating around in a beaker. So that's always kind of random unless you get a catalyst involved. But we can control how much energy they have when they collide. So if matter of fact, let's do this. I need 2 volunteers, Renee and you, Abraham. Okay. Here, hold this. And hold this. Now, let's say that Abraham is a molecule and Brene is a molecule. And we, the chemists, want there to be a double replacement reaction where Abraham, the molecule, gives this part of himself to Brene, and Brene, the molecule, gives this part of herself to Abraham. And so this is what we're trying to get to have happen in a beaker. It's a double replacement reaction, okay? But the bummer is that in order for that to happen, they would have to run into each other. They would have to run into each other with these parts running into the other. So Abraham, hold your bottle at arm's length, and hold your thing at arm's length. Now, come here. They would have to bump into each other like this for a chemical reaction to happen and these things to get exchanged, and then they go about their way, right? This is a chemical reaction that just happened, which is great. But, turn around. Now, don't hurt him. But run into Abraham in this orientation, right? Now, in that way, he can't exchange his molecule part because it's not facing her, right? So the orientation wasn't right. So there would be no chemical reaction there. Okay, face each other again. And now run into each other very slowly. They run into each other very slowly. There's not enough reaction energy in the collision to make this happen. So they would just bounce off and be like, hey, it's better luck next time. Okay? Thank you very much. Appreciate it. So in order for a chemical reaction to happen, the molecules have to bump into each other in the right orientation so that the active parts collide. And they have to run into each other with enough energy so the reaction happens. Okay? When the above collision happens, then the situation at the moment is called an activated complex. So when Brene and Abraham ran into each other with enough energy and were able to exchange their portions with each other, then that moment of exchange is called the activated complex. The reaction is happening right now. That split second, that's the boom. That's when it happens, right? And then they would wander off from each other having collided, and the reaction happened, and yay. But that activated complex, that moment of exchange of atoms, is what we're trying to get to happen in reaction kinetics when a reaction happens. Okay? And that would be the peak of the graph, is the activated complex. Okay, so I've got a little picture of it here. The energy needed to get a reaction to happen is called the activation energy. That's the top of the peak. And at the activation energy, we're breaking old bonds and we're making new ones. So here we have a little animated GIF there of one molecule running into another and a reaction happening where the...
So it lost the protons or something?
Yeah, these are all atoms. So one molecule collides with another molecule and it kicks off an atom from the one and there's a new bond formed. So here we have an old bond that needs to be broken, and here we have a new bond that needs to be formed. And they have to run into each other in the right orientation, and they have to run into each other with enough energy. So if the little red molecule cruised into the back end of the green one, but without a lot of energy, just kind of like, hey, how you doing? Then there's not enough collision energy there to make the reaction happen. Or if the red one just wailed into the green one, but they're not facing the right way, then they're not going to be in contact long enough for the bonds to be reorganized. So they have to collide the right way, and they have to collide with enough speed. And when that happens, we've achieved the activation energy. And that split-second moment when the red one and the green one are in contact before this one goes away, that's the activation complex. That's the split second in time when the reaction is happening. Okay? So that's kind of the terminology here that we're looking for. Okay? Now, a reaction rate is an expression of how fast a reaction occurs. And when we talk about how fast a reaction occurs, we're talking about how many moles per second can we process. So a mole is a unit of volume of stuff, and we are looking at how much stuff can we process per second. So in your very slowly happening chemical reaction in your medicine cabinet of hydrogen peroxide turning into water and oxygen, it happens, but it happens like not moles per second, but moles per decade, like really slow. But it is happening. But then the chemical reaction of a firework going off is tens of moles per second, like really fast this occurs. And so we're looking at how fast is something happening, and this is the rate that we use, moles per second. We can influence a reaction rate. We can control or influence how fast a reaction happens by increasing the concentration. So picture, again, not just one Abraham and not just one Renee trying to bump into each other and exchange atoms. But if we were to take 25 Abrahams and 25 Renees and put them in the room and have them walk around and bump into each other, there would be a lot more occurrences of bottle to jar run into each other and then the exchange happening. But if there's only one Abraham and one Renee in the room and they're just randomly walking around without trying to run into each other, they wouldn't run into each other very often, okay? But the more of each kind of molecule you put in a small space, then the more collisions there will be, and the more likely that one of those collisions will get the job done and we'll have a reaction start. Okay? So concentration does it. Temperature does it. The faster the particles are moving, the more likely they are to run into each other with enough energy to make the reaction happen. And remember, temperature is just the speed that particles are moving. So low temperature, things are just kind of moseying along out for a Sunday cruise, and just not really hurried when they bump into each other. It's, hey, how you doing? And there's no reaction that happens. But if you crank up the temperature, then the particles are all moving faster. And when the reaction and when the collisions happen, if they are of the right orientation, they will have enough energy to make the reaction happen. Okay? So temperature controls the speed at which they collide. Concentration controls how frequent the collisions are. Surface area. If you have 25 Abrahams and 25 Renees, but all the Abrahams are stuck shoulder to shoulder, like locking arms and holding their little thing, and all the Renees are stuck together, arm in arm, holding their little thing, then these blocks are all moving around together. Now, when the blocks happen to run into each other, you're going to get a reaction at 2 or 3 places. But the ones in the middle are never going to react because the ones in the middle are protected, are insulated from the reaction possibility by all of their friends. So the smaller you can get the particles, the more reaction will happen, which is why you can burn sugar, but you've got to get it really hot, and then the sugar will start to burn. But if you've ever tried to burn powdered sugar is almost flash powder. It burns real quick because the particles are so much smaller, it's a lot easier to get the sugar to ignite. So smaller particles increases the surface area, increases the likelihood that things will run into something else and get a reaction to happen. So surface area or particle size controls how many of these things can potentially react. And then the last factor for a reaction rate is the presence of a catalyst. A catalyst is something that increases the reaction rate by lowering the activation energy and are not consumed in a reaction. And that's not the first time you've seen that word. You met catalysts back in physical science, and you've probably heard the word catalyst long before this. A catalyst is something that speeds up a chemical reaction. And the way that it speeds up the chemical reaction is by controlling orientation. All of these other things can't control orientation. Concentration, temperature, and surface area can't control that particles run into each other in the right orientation. But a catalyst does. A catalyst would grab an Abraham, grab a Bernet, and say, here, face each other, now run into each other. Okay, chemical reaction. Yay. It's like a matchmaker, right? Okay. And so a catalyst controls orientation. It grabs a molecule and spins it to the right direction. The other one spins it in the right direction and makes them run into each other. When a catalyst does that, it speeds up the chemical reaction because now all of the collisions are properly oriented. And so the molecules don't just bounce off of each other, the reaction happens. And because that's all they do, catalysts are not consumed. A catalyst can create one reaction and then another one and then another one and then another one because they're not used up. They aren't spent in that reaction. They can grab another molecule and run them into each other in the right orientation over and over and over again. So they're not consumed. They lower the activation energy, and they do that by having collisions in the right orientation. Okay, so these are the 4 things that influence reaction rate. Do you have any questions at this point? 4 things that influence reaction rate. Catalysts, because they influence orientation. Concentration controls the number of collisions. Temperature controls how fast the collisions are. Surface area or particle size has to do with insulating molecules from the reaction. Any questions? Okay. So here's an example of a catalyzed versus non-catalyzed reaction. Here I have the reactants. Here I have the products. The delta H in this textbook uses delta E that I lifted this from, but that's okay. The delta H is the same. It still starts and ends at the same amount of energy. And they both require an activation energy to get going. The difference is, without a catalyst, I've got to go way up here. I've got to add all this energy to it for the reaction to happen. And then I get a bunch of energy out going down to the products. If I add a catalyst, I start and end in the same point. But I don't have to add as much energy because more of my collisions are in the proper orientation. So the activation energy is less. So this is a catalyzed reaction. My increase in energy to the catalyzed activation complex is small. So there's a smaller hill on the roller coaster, but you still get to say V and wind up at the same place. Okay? So this is the difference between a catalyzed and an uncatalyzed reaction. Now, some reactions don't happen all in one step. Oops. Some reactions don't happen all in one step, and some catalysts work by breaking a reaction into a whole bunch of small reactions and catalyzing each of those little small reactions. So you could have, from reactant to product, this is an exothermic reaction. It will occur spontaneously, but it has a very high activation energy. You've got to add truckloads of energy to it for it to happen. And then it does happen, and you get all that energy back, and you wind up at a lower place. But there's a catalyst that can come along, and the catalyst takes one big step and divides it into a whole bunch of smaller steps that have lower energies. So it can catalyze one step, and then catalyze it again, then catalyze it again, catalyze it again, catalyze it again. And it breaks this big chemical reaction into smaller bite-sized steps and catalyzes each of them so that my highest point is still much lower than the other, even though I'm turning one reaction into like 6, or 1, 2, 3, 4, 5. Okay, 5 reactions. So I've taken one reaction, I've broken it into a bunch of smaller ones, and I am saving a bunch of energy by doing that. Okay, still starting and ending at the same place, but spending less energy to take one big step and make it a bunch of small ones. And then this is an example of a reaction that is being catalyzed by different enzymes. And so it's the same reaction. It doesn't matter what the reaction is. It's the same reaction. And we're going from the reaction of the reactants, I'm sorry, from the energy reactants to the energy products. But what we're looking at is different kinds of catalysts that are breaking the reaction into different pathways. And then we're analyzing how many different pathways it takes. So this is just another picture of multiple different catalysts doing the same job. That's why we have 2 lectures this week. There's a lot to say. Okay? Okay, so I've already said J. You haven't written it down yet, but catalysts work by prearranging reactants into the right orientation so that it's easier to form an activation complex. They have to do with orientation. Okay? And so they bond with something else, and then slam them into each other, facing the right way. Enzymes are catalysts in biological systems that are made up of proteins. So we talked about catalysts and enzymes in biology. This is just a reminder. You've already had that information. A catalyst that is involved in a biological reaction and is made up of a protein is called an enzyme. You are an amazingly complicated chemical machine. You're more than that, but you are that. And the chemical process is happening in living systems, and you in particular are absolutely fascinating, and God is an amazing chemist. And the reactions that happen in you without an enzyme would never occur. You have monstrously high reaction energies for some of the chemical reactions that are occurring in your body. And the orientation that these big molecules have to run into each other in would never happen, or would happen so rarely that without enzymes, life would not be possible. Because the life processes have to happen, they have to happen quickly, they have to happen over and over again. And enzymes are the machines, the protein machines, that keep the incredibly complex chemistry of you happening. And so the protein catalysts are called enzymes. And then there are things called inhibitors, substances which interfere with the normal functioning of a catalyst. Some of these are natural, some of these are pharmacological. For example, people with diabetes, they don't process sugar well. And so sugar levels build up in their blood. And one way to control too much sugar in your blood is to control your diet and not eat a lot of sugar. The other way is to inject yourself with insulin. And insulin is an enzyme that moves the sugar into the cells and out of the blood so that the cells have the sugar that they need and it's not just laying around in the blood. Okay? That's adding an enzyme. The other way is to inject yourself with an inhibitor that stops your body from reabsorbing the sugar out of your urine. So your kidneys are always removing sugar from your blood, all the time, and putting it in your urine. But your body, for healthy people, you don't want to pee out the sugar because you need that for your life to happen. So there's an enzyme that fishes the sugar back out of your urine and puts it back in your blood. So it's pulling the good stuff out of your urine and putting it back in the blood. Well, if you have diabetes and you've got too much sugar in the blood, another way to lower the sugar is to stop the enzymes from reabsorbing the sugar. So now you pee out your sugar. and that lowers the amount of sugar in the blood. So that's an inhibitor. So enzymes and inhibitors are proteins that can influence chemical reactions. These ones speed up chemical reactions. These ones slow down chemical reactions by stopping an enzyme from working, by getting in the way of the enzyme. Okay? There are natural inhibitors. Most of the time, inhibitors that you will run across are drugs that specifically go in to turn off something that's going wrong in the body. Okay? So catalysts, enzymes, and inhibitors. Here's a little model to help you understand this. Pause my recording.